The next time the scientific community returned to the topic of Bohr and the atom was only in 1928. That is when Paul Dirac started calculating the motion of an electron around the nucleus, wrote the famous Dirac equation, and solved it. The equation can be used to calculate not only the energy of electrons that move around the nucleus of hydrogen atoms, but of any atom. Dirac asserted that this equation calculates the energy spectrum, indicating a continuous spectrum where the energy becomes greater than m sub 0 c squared of the electron mass, electron rest, or less than minus m sub 0 c squared. And only in this interval between plus m sub 0 c squared and minus m sub 0 c squared can the electron take discrete values. Only here are atoms possible, because it is necessary that it takes on a discrete value revolving around the nucleus. This part is called continuum, also referred to as the Sea of Dirac or a vacuum. We will return to the word vacuum several times, and I would like us to understand that a vacuum is not emptiness at all. Generally speaking, the concept of the vacuum goes as far back as ancient Greece, when philosophers also said that a vacuum is not a void, but that it is a substance in which we can distinguish one object from another, and in which we can see how one object moves to another. This is how things happen within the atmosphere. In quantum mechanics, or it is better to say quantum electrodynamics, these are the states that are continuous, that are occupied and cannot take on different values, and are vacuums. Our world exists in this gap here. Now let's see what happens when we move to heavier elements. Here is hydrogen. Here is its binding energy, 13.6 electron volts. Here is the atomic number of a nucleus, or the atomic number of an atom. And as we move, this type of energy starts to increase, the binding energy of the first electron. And it increases according to Dirac's equation, the square root of 1 minus alpha z squared, where alpha is a fine structure constant. The fine structure constant is a constant that speaks of the strength of the electromagnetic interaction. We will return to the constant values of quantities later. It is easy to understand that when we reach Z, the fine structure constant is about 1 over 137. And when we get to Z equal to 137, this value becomes equal to 0, at which point there is no solution. The electron has fallen on the nucleus, and there is no further movement. That is what happens if the nucleus is a point charge. This is where the superstrong field comes in, and where this whole theory ends. In fact, the nucleus is not a point, it has a specific size. And if it has a specific size, then the charge would be spread out within this circumference. If it is spread out, it means that there is no super strong field, and therefore the picture would be a little bit different. Although we have come very close with our super heavy elements to this critical situation. However, the situation is different. The energy level goes further, all the way down to 0. Here at 0, it would seem, is where the end should be. In fact, what was surprising was that the equation still offers a solution when the results drop below 0. That is, when we go into negative energy. Although the word negative energy is some kind of strange quantity, what does negative energy mean? Dirac confidently offered a solution and said that no, it would be okay unless the electron is not an electron, if the electron is an anti-electron, or if the electron is a positron. And he then predicted antimatter for the first time, that an electron can have an anti-electron. Then we will see that a proton can have an antiproton, and so on and so forth. In short, life continues. It goes on until it collides with the border of this continuum, a negative vacuum, where this atom becomes unstable in relation to another atom and positron, roughly speaking. And in this super strong field, an electron is ejected from the negative continuum, sits in orbit, forming a hydrogen-like atom, resulting in the fact that the vacuum becomes charged. And in order for it to become neutral again, a positron is emitted from the positive continuum. The graph is clear. There is nothing in the vacuum. And as the charge of the nucleus increases, suddenly at a specific moment, an electron appears, which sits in orbit around a bare nucleus, very heavy, about 172 to 176. And a positron is emitted from the emptiness, which goes to infinity. From the point of view of Bohr's construction, the nucleus is in the middle, around which the electrons orbit, and this movement was calculated not only by Bohr, but also by Dirac, calculated by way of quantum electrodynamics, which takes into account the fact that the electron has half-integer spin. It turns out that an atom can be very large. Its atomic number can even be as high as 176. But actually, this is not so, because the limit is not determined by the atom, not by the structure of the atom, not by the destruction of Rutherford's structure, but the limit is determined by the stability of the nucleus itself. And therefore, this question should be transferred to nuclear physics in order to see where the stability of the nucleus itself ends.